This is a continuation in our series of videos in which we're looking at solutions to questions from CSEC Physics of 2024. All right, and in this video, we're going to be looking at question 5. And question 5 deals with electricity and magnetism, particularly electric fields and magnetic fields, and so on. All right, now let's jump into the question. Um, First part of the question says 5 part A1, define the term electric field. Now, what is an electric field? We can say that an electric field, an electric field is a region of space around a charged particle or object in which another charged particle or object experiences, or we could say experiences or feels a force, right? So this is exactly what an electric field is. Now, it is important that you mention that another charged particle must experience a force, because obviously, if no force is felt by another charged particle, it means that the field does not exist to that particular region, right? Now, if an object is charged or a particle is charged, what it means is that there is going to be a space around it where if another charge finds itself within that space, a force will be exerted actually on both charges, right? But of course, the electric field is not infinite. And so you will have a region where no force is felt, and that basically means that the field does not extend to that region, all right? So once again, an electric field is a region of space around a charged particle or object in which another charged particle or object experiences or feels a force, all right? And of course, with that we go into part 2 of the question. Now, part 2 of the question says figure 10 represents the electric field between and around two charged objects. So see figure 10. We have two charged objects apparently, A and B, and we see the field lines, and we can also see the field direction. The arrows typically point from A to B, and the question now tells us to state the type of charge at object A. Now, how do we use this diagram to deduce the type of charge at object A? We use the direction of the field lines. We know that electric field lines originate on positive charge and they terminate on negative charges. So the mere fact that the field lines are actually pointing from A to B, then this tells us that A must be a positive charge, right? So therefore A must be a positive charge due to the fact that the field lines originate on charge A and terminate on charge B, right? So therefore, the charge at A is a positive charge. Now, the next part of the question deals with a magnetic relay. And it says a magnetic relay is used to switch on a circuit carrying a large current. Figure 11 shows an electromagnet used in a magnetic relay to operate the starter motor of a car. So what is shown is we have a primary or input circuit in which there's a switch, there is a battery or a cell, right? And of course we have a soft iron core around which we have a coil of wire, which is a part of the external circuit, right? That's a primary input circuit. In the secondary output circuit, we see that we have a soft iron armature, we have some metal contacts, there is a starter motor, and of course conducting wires hooked up to the battery as well, right? Now, how does this operate? We're talking about a relay, and the word relay, of course, is synonymous, for instance, with the sport of track and field. In track and field, of course, there's a 4x1, 4x4, 4x8, a medley relay, and in a relay, a baton is normally passed from one team member to the other, right? And so the word relay has a similar, meaning when it comes to these type of situations, right? So let's explain what happens here. Now, when the switch is closed, what it means is that a current would flow in this external circuit. So this is a positive terminal of the battery or the cell, and therefore the conventional current I would flow in that direction. Now, as the current flows, what it does is that it creates an electromagnet. So the soft iron core with the coils of wire wrapped around it becomes an electromagnet. Now, this electromagnet is able to attract the soft iron armature in the secondary circuit. When it pulls on the soft iron armature, the metal contacts are now able to touch. They touch and they basically complete the circuit, and this causes an electric current, a much larger current than that in the primary circuit, to flow. And this basically is how the starter motor operates, right? So once again, when the switch is closed in the primary or the input circuit, a current flows. A current flows around the coil, within which we have a soft iron core. That combination of the soft iron core and the coil creates an electromagnet. And this electromagnet is able to attract the soft iron armature of the secondary circuit, and this causes the metal contacts to touch. Now, when the metal contacts touch, it means that the circuit is now complete and the current can flow. And of course, a much larger current now flows in the secondary circuit than that which would have flowed in the primary circuit. And this basically is the principle of the magnetic relay. All right. So that was part C. Now let's move on to part D. Now part D says Figure 12 shows a wire connected to a center zero galvanometer. The wire is placed between the poles of a permanent magnet. Now, what is the purpose of a galvanometer in a circuit? And what is a galvanometer? A galvanometer basically is a device that is used to detect the presence of an electric current, right? And in this particular case, we're told it's a center zero galvanometer, right? What exactly does that mean? The center zero galvanometer operates in such a way that when there's no current flowing in the circuit, the needle would be centered on zero, right? So when there's no current flowing, or when it does not detect a current flowing, let me say that. When it does not detect a current flowing, it is centered on zero. However, when it detects a current, the needle will then deflect. It may deflect to the right based on the direction of the current flow, or it may deflect to the left based on the direction of the current flow. Now, the amplitude of the deflection will basically give an idea of how large a current is, right? So if, for instance, we have a tiny current flowing and the galvanometer is sensitive enough, you may see a small, slight deflection. However, if that current is increased, then you're likely to see a larger deflection, which of course is indicating that a larger current is flowing, right? So we can use, say, for instance, the amplitude or the degree of the deflection to give an idea of how large current is that is actually flowing in the circuit. All right. Now, for the most part, we want our galvanometers to be sensitive, which means that they could actually respond to even tiny currents that actually flow in the circuit. If the galvanometer is not sensitive enough, it means that there might be an induced EMF and there might be an induced current flowing in the external circuit, but it might not detect it because it is not sensitive enough. And so we normally see galvanometers in questions being described as being sensitive. This one was not, but of course, that is a reason why we would need galvanometers to be sensitive. All right, good. So let's examine the circuit now. So here we have the north pole of a magnet, and of course we have the south pole, and we can see that the field lines run from north to south as they typically do. Within that magnetic field, there is a metal conductor, and of course, a metal conductor is connected to an external circuit, which of course includes connecting wires and the center zero galvanometer. All right. So the question tells us now, state what is observed on the galvanometer when the wire is moved in the direction shown by the arrows. So in this first case, the wire is moved back and forth parallel to the magnetic field. And what happens? Essentially, nothing happens in terms of a deflection in the galvanometer needle. When the wire is moving back and forth parallel to the magnetic field, no field lines are being cut. And this therefore means that no EMF is being induced. And if there's no EMF being induced, it therefore means that no current can flow. So no current flows and the galvanometer does not deflect. So we can basically say that the galvanometer does not deflect. So we're talking about what would be observed. The galvanometer does not deflect. Galvanometer. right? So say that the galvanometer does not deflect, right? Good. Now let's move on to the next part of the question. The next part now basically says that now we're supposed to state what is observed on the galvanometer when the wire is now moved upwards through the magnetic field. So in this case now, the wire is going to be moved upwards, right? So basically, let's say just put an arrow there to show the direction of movement of the wire, right? Right, so this wire is now moved upwards. And now what do we expect to happen? When the wire is moving upwards, it means that field lines will be cut, right? Field lines will be cut in a similar manner like you take a knife and you slice a piece of cheese or you cut a slice of bread. So the field lines will be cut by the conductor. And this relative motion between the conductor and the magnetic field, with the field lines being cut, will cause an EMF to be induced. An EMF would be induced, and because the conductor is part of an electric or part of an external circuit rather, it means that it will cause an electric current to actually flow, and the galvanometer will be seen to deflect. Now, the question may not have required us to say predict the direction of the current flow, but we can do it using Fleming's right-hand rule. Now, according to Fleming's right-hand rule, if you place the first finger, the second finger, and the thumb of your right hand in such a way that they are mutually perpendicular, then with the first finger pointing in the direction of the field. So the first finger or the index finger, this one, must point in the direction of the field, right? The thumb must point in the direction of the motion of the conductor. And I'm stressing certain syllables in those words. So the first finger must point in the direction of the field, right? The thumb must point in the direction of the motion of the conductor. And then if those two are achieved, then it means that the second finger will then point in the direction of the induced conventional current, all right? So first finger, field. Thumb, motion of conductor, direction of motion of conductor. And that leaves the second finger pointing in the direction of the induced conventional current, right? And of course, it means electrons will flow in the opposite direction, right? So let's do this. Now, the field is running from north to south. So we must rotate our hand so that the first finger points from north to south. Conductor is moving upwards. So my thumb is pointing upwards. And as you can see, well, you're not seeing my second finger, my middle finger. It is pointing towards me. And therefore, what this means is that the current will now be flowing from the positive end of the conductor in an anti-clockwise direction, right? So once again, with my first finger pointing north to south in the direction of the magnetic field, my thumb pointing upwards to reflect the direction of motion of the conductor. My second finger or my middle finger is pointing towards me, that is out of the screen, and this therefore means the conventional current is flowing in that direction from the positive end of the conductor, and this would be in an anti-clockwise direction around the circuit, right? So in that particular case, the current flows in that direction, and of course, it means that the galvanometer needle will reflect this. Okay, good. Now, what do we expect now when the conductor is now moved downwards through the magnetic field? We would expect that the direction of the induced EMF will change and the direction of the induced current will be reversed. But let's actually just use Fleming's right-hand rule to confirm this, right? Let's do that. So let's change the direction of our arrow, change that. So this time I'm going to show the arrow pointing downwards, right? Right. So we have the arrow there now indicating the direction of motion of the conductor. So once again, we're going to be using Fleming's right-hand rule. So first finger must point in the direction of the field. The thumb must point in the direction of the motion of the conductor. And if those two are achieved, then that will leave the second finger pointing in the direction of the induced conventional current, right? So let's do this. So the field, once again, is from north to south. We do that. But this time, the conductor is being moved downwards. So we must rotate our right hand so that our thumb is pointing downwards, right? So we've done that. So our field, first finger pointing from north to south. Our thumb is pointing downwards, and this leaves the second finger pointing into the screen, and therefore this means that the conventional current will be flowing in that direction, right? So in this case, the conventional current would be flowing this direction, where it will be leaving the negative end. You can see the minus sign in the diagram, right? Minus there, and there's a plus sign here. It leaves that end, and therefore the current now flows in what's that? Clockwise direction. Okay, so we've seen that by using Fleming's right-hand rule, we'll be able to predict the direction of the induced conventional current in the external circuit, and of course, predict what will happen in the case of the galvanometer needle. So in this part now, where we say that, in the first case, of course, well, we didn't mention it, but we didn't write it, but the galvanometer, of course, deflects in a certain direction. And if you notice, we have one mark for that. So for the second, for part three, we should mention that the galvanometer would deflect in the opposite direction. So for part two, it may have been sufficient to say that the galvanometer needle deflects. But for part two, for the extra mark, you probably were required to indicate that the galvanometer needle would deflect in the opposite direction to that in part one, right? So we could probably just say that the galvanometer needle deflects and in part three, we'd be required to say that the galvanometer needle deflects in the opposite direction, in the opposite direction to that in part two. All right. And that is basically it. So that's what would have been required of us for this particular question, right? So this question again was question 5 from CSEC Physics 2024. It dealt with electric fields, magnetism, magnetic relay, and of course magnetic fields, electromagnetic induction. We're able to, go through the question and do what was required. All right. So this is the end of this question.